Alright, we're gonna get started. Alright, team's ready to get started. Good evening, everyone. I would like to thank you for coming out to our senior design presentation. We are the BPMI heatsink redesign team, and before we get started, I'm going to do a brief introduction of everyone in the team so far, so let's get started. My name is Josue Rosario. I'm the team lead of the project for both semesters. You're going to meet everyone else throughout the presentation, but first I'm going to introduce each subgroup independently. So first was the thermodynamics and heat transfer calculation subgroup. What this group did was mostly do a lot of the research at the beginning of last year. They would look at different designs depending on what BPMI wants us to accomplish, and then we'll apply those to different designs for a heat sink. And once the design is picked, they'll do some mathematical calculations to determine optimal spacing and size of pins that we can use for the Creo team, which is next. So next team is the Creo modeling team. They took the design proposed by the thermodynamic team and designed them into a CAD program. The programs we used was Creo modeling and also SolidWorks. The last group is computational fluid dynamics subgroup. They took the Creo models and put them into a computational fluid dynamic or CFD program. In our case, it was Siemens Star CCM. They pretty much ran simulations to emulate the same exact environment that the heat sink would be in. So BPMI's main goal for us was to redesign a heat sink using complex geometries made possible by additive manufacturing and validating our results using a computational fluid dynamics program. The first task was to design a heat sink with an improved pressure drop while maintaining the same thermal performance as the original design. For those who don't know, a pressure drop is the difference in pressure between 2 points of a fluid system. So in our case, pressure we measured from the front of the heat sink, where the fluid enters the device, and the back of the heat sink, where the fluid leaves the device. The reason why you want to improve pressure drops is because an improved pressure drop allows for a more effective heat sink. The second task that BPMI had given us was to design a heat sink where to reduce volume while maintaining the same pressure drop and thermal performance of the original design. Now for us, volume wasn't the amount of material, because weight didn't matter for us. It was more of the size of the material itself. So you're going to see later some dimensions change based off of what BPMI has given us. Our third task was a stretch goal. So pretty much it's a goal that BPMI would like us to obtain if given time. So that goal was to 3D print a model for the task 1 design, which was improved pressure drop, and test it in a wind tunnel or experimentally. This is, as you can see, this is the wind tunnel. We'll talk more about it later in testing, but we'll get to that eventually. So I mentioned multiple times the original design. What does this original design look like? Well, thankfully, I got a picture right here. And if you can see very well, it's actually in the middle of the room. I'm pretty sure people in the back probably can't see it at all, so Josh is saying no. So yeah, so we got a picture up here to make it easy. So this is the design that BPMI has given us. As you can see, it gives a sine-like curve, but doing more research, it's pretty much flat plates going across the heatsink and is used mostly in computer heat sinks. It's not very unique compared to other heat sinks, but it does give good heat transfer. As you can see, the fins are compact, close together, therefore giving a lot of surface area, therefore more heat transfer is allowed. But because the pins are so compact, there's a great pressure drop that goes along the heatsink itself. Now here are schematics that BPMI has given us. There's 2 things I want to point out that will be valuable later in the presentation. First is the 3 shaded areas here. These are known as the hot spots. So the heatsink will be receiving heat at these 3 hot spots from the device it's connected to and dissipated through the fins. Another thing that's unique is that the heatsink itself is upside down. I would like to point this out because you're going to see some simulations where the heatsink itself is right side up. And since we're pushing air through, it's forced convection, so heat transfer and pressure drop do not really change if the heatsink's upside down or right side up. Now the reason I bring the dimensions to your attention is because both tasks had different dimensions. So for task 1, pretty much all the dimensions you see here remain the same. Nothing really changed with the heatsink. But for task 2, we see a change in dimensions. So the dimensions circled in red tend to decrease, while the dimensions in green would remain the same. It's important to note that these 2 dimensions closest to me, representing the depth and the width of the heatsink, were decreased by 0.75 inches, which was given to us by BPMI, while the height of the fins on that side is supposed to be minimized as small as possible. Now that you know the introductory of the original design and what we're supposed to do and what will change, I'd like to hand it off to Liz, who will talk about the different design concepts we have.
Hi everybody, my name is Liz and I was part of the thermodynamic calculation subgroup. So last semester we came up with a bunch of different variations of designs for the different tasks. For the first design, we primarily focused on ellipses and airfoils this semester, and we have a couple of little models going around of a bunch of different variety. But those ellipses and airfoils we looked at, and in preliminary CFD calculations this semester, we discovered that airfoils were much better at reducing the pressure drop than the ellipse design. So we worked on those and we tweaked the design a little bit to see how we could accomplish improving upon that original design with an airfoil pin. For the second task, we focused on pin-fin splitter plate designs. And we did a few variations on those. You'll see on the right, each one has a little pin and then like a plate attached to the back. So we played around with varying the width of that plate as well as the length of that plate to see if we could match that heat transfer in the original design. But primarily what we focused on this semester actually was the design on the left, which is what we call an ice cream cone splitter plate. It's officially called a V-shaped splitter plate, but for obvious reasons we call it the ice cream cone splitter plate. And that one was much better in calculations with heat transfer and reducing the pressure drop. So we focused on that more this semester. Some of the problems that we encountered in our calculations and experimenting this semester were that, as you can see, the original design is a lot of surface area. It's essentially a solid block of material. So trying to match that with any pin design was very challenging to get that same effective heat transfer area. Another problem that we faced was a lack of mixing flow. It wasn't, with the pins we had, they would just split along the side there in the front and then just go down the side of each little channel, so to speak, and it wouldn't hit the pin behind it. So we played around with the dimensions between those pins and moving those around, and as well as staggering the pins to make sure that it would hit all of the pins and get maximum surface area. So for the airfoil design, the first thing that we tried was increasing the density of those pins. We significantly increased that in order to maximize the surface area. And then we also tried a staggered design as opposed to inline to help reduce that pressure drop even more. So this was our preliminary airfoil design, but when we were still falling short of that surface area, we tried doubling the width of the airfoils to give us more surface area while keeping that same pin density, which really helped to increase the heat transfer. And with this design in CFD calculations, we actually were able to improve upon the original design. So now Sadie's going to tell you a little bit about our designs for reduced volume.
Hi, my name is Sadie Hill, and we are now going to talk about task 2. So task 2, as mentioned before, was reduction of volume. And so in order to do this, we tried a few different approaches. Primarily, we ended up going with a pin-fin splitter plate design, as seen on slides before. So our main variable then was, are we going to do these as staggered pins or inline pins? And as also mentioned before, if you have a bunch of pins in a line, there's a lack of mixing of flow. So we ended up experimenting with inline and staggered in order to achieve best results. So we did find that there was a trade-off in the staggered ice cream cone designs with inline pins for like the crucial values of pressure drop and heat transfer. So the staggered plate design then had less plates in it, but it had more pins. So we decided eventually that inline was in fact better because we were still able to get the effective needed heat transfer, and we were able to maintain a good surface area. So as you can see here, this is the design for volume reduction that we talked about, and as you can see, there's the plates and the pins, and we, as mentioned, did not go with the staggered in order to increase the amount of surface area. So now Andrew will talk more about the original design.
Hello, my name is Andrew Egger. I worked as part of the Thermo team as well as our modeling team. So the original design, as noted, is a very large design, and it caused us a lot of issues within Creo 7. Most notably, the rendering time was significantly high and would not allow us to edit the part as needed. This is most likely contributed to lacking computing power, as well as the regeneration errors is also a factor of that. Those very small complex features within each of the fins, going back and forth, that was also a significant contributor to the regeneration errors we experienced. So in order to fix this, we transitioned our model from Creo over to SolidWorks. SolidWorks is able to provide us a very stable platform in order to finish modifying and complete the original design. To tail off of that, some of the adaptations we had to make into our computational fluid dynamics program. You can see on the right, there's a slit in the top of every fin for our simulation model. This is able to create one fluid flow field, so we could run the simulations in the CFD software. Without that, under each fin, there would be a separate flow field, and it would not be optimal for simulation. On the left, you can see there's some added material underneath of each fin. That is to simulate a spec'd solder connection at the bottom of each of them. This allows for heat to be transferred from the base into the fins, as well as providing a little bit of structural support. Finally, all of these models had to be modeled as assemblies. This is due to BPMI telling us that the fins and the base plate have different thermal conductivities. Modeling all of these as assemblies, we're able to help accomplish that. So now I'll hand it over to Max to talk more about computational fluid dynamics.
Hi, my name is Max Wilson. As Andrew stated, I'm just one of the team members on the computational fluid dynamics side. Computational fluid dynamics, if you don't know anything about it, it's basically just using computers to model fluid flow over solid objects. So in our case, the fluid flow was air, and the solid object was the heat sink. Anyway, we used a couple of different machines, a couple of different computers to do that. And as Andrew also talked about, our machines weren't very powerful. Here are some of the given parameters that we used for our computational fluid dynamics and some of the stuff that BPMI gave us. All of our models were run at 60, 100, and 140 CFM, which means cubic feet per minute, if you don't know that. And then fluid properties, we were given an inlet temperature of about 50 degrees Celsius and inlet pressure of about 101 kilopascals, which is atmospheric pressure. Now, some of our material and physical properties, as I said before, we didn't have much computation power, so we ran all of our models in 1/8 sections. This allowed us to get a good comparison between the different designs that we had. Also, we applied 750 watts to the base of all these designs to try and stay uniform across them, and so that we can get, again, that comparison between the different designs. Now, BPMI gave to us the different material properties. For the fins, there was a thermal conductivity of 220 watts per meter Kelvin, and a base conductivity of 550 watts per meter Kelvin. Here are some of the solution models for our CFD. Solution models is basically what the CFD program uses to solve the different equations that it needs to solve the fluid flow. So for the fluid itself, it used an ideal gas, three-dimensional flow, steady inlet velocity, gravity, and a K-epsilon turbulence model. The K-epsilon turbulence model is a model used oftentimes for conjugate heat transfer simulations such as this one, and is good for our situation. We also use segregated flow, which is a good solver for our situation because we don't have very high fluid flow. You would use a different type of solver if you were to do stuff on supersonic speeds or anything like that. For our heatsink model, we used the solid constant density thermal resistance and segregated energy models. We use the segregated energy model to stay consistent with the fluid model, otherwise you'd get errors between the two. Here are some of our original design results. Like I said, we're running this on 1/8 sections of the heatsink, and these results that you're seeing here are done at 60 CFM. So we got a 50 Pascal pressure drop across the 1/8 section of the original design, and thermal resistances of 0.089 Kelvin per watt on average, and then a maximum of 0.093 Kelvin per watt. Now I'm going to hand it over to April to talk about some more results.
Hi, my name is April Huffman, and I was the other member of the computational fluid dynamics team. And as Max said, I'm going to be walking you through some of the results of our designs. So for our designs, we decided to run models through CFD with different fin shapes and sizes to see how they compared against each other to pick the optimal design. Some of those were ellipses, circular fins, and airfoil fins. For these models, we chose to run them on geometries with the numbers of fins ranging from 1 to 15 fins. But for the results shown here, these are the results for the geometries of 1 row and 5 fins, as you see pictured here. All of these simulations were again run at 60 CFM. And it's important to note that the circular fins had a larger diameter and smaller spacing between the fins, which is the reasoning for the much larger pressure drop for the circular fins that you see here. And as you can see in this picture, you can see the spacing is far smaller between the fins and the diameters are much larger. So from these results, we can clearly see that the ellipse fins produced a pressure drop of 6.3 pascals. The circular fins produced a pressure drop of 72 pascals, again due to that smaller spacing and larger diameter. And the airfoil, as you can see here, produced the best pressure drop for our case scenario of 1.2 pascals. Now on to some of our pressure drop design results. In light of the airfoil pins giving us the lowest pressure drop, we decided to take that design and optimize it to further optimize the thermal performance of the heatsink. As mentioned before, we did this by running models of airfoils with normal spacing, high density airfoils, and then double thickness airfoils, as Liz mentioned earlier. As you can see from these results, all of them were staggered as that produced the best pressure drop and thermal performance. And again, all of these were run at 60 CFM over an 850 heat sink in order to compare it to our original design. These results rendered the original, or the normal airfoil with normal spacing rendered a pressure drop of 4 pascals, while the high density airfoil produced pressure drop of 7 pascals, and the double thickness produced one of 11 pascals. And so even though we didn't quite hit the resistance of, or didn't quite match the resistance of the original design, as you can see there, you can also see that we didn't even come close to even matching the pressure drop of the original design, which is a very good thing. Moving on to some of our results from the reduced volume designs. Again, all of these simulations were run at 60 CFM over an 8th of the heatsink. And as you can see, even though the staggered designs produced a slightly lower pressure drop than the inline design, our team decided based on these results that the inline would be optimal given that its resistance and thermal performance was better than the staggered design. We attributed this to the fact that the plates produced better thermal performance than just adding more fins and staggering them, because that would require us to remove some of the plates to reduce that volume. And then lastly, you just have a graph here of the pressure drops, comparing all the pressure drops of our designs to that of the original design. This is over the CFMs of 60 through 100 and 140. As you can see, the pressure drop of our designs don't even come close to, again, hitting that pressure drop of the original design, meaning that if BPMI were to take these designs and optimize them, they would have lots of room to experiment with different fin shapes and sizes and densities in order to optimize that thermal performance while still maintaining that low pressure drop. Now I'm going to hand it over to Alyssa, who's going to be talking about some of our tests.
Hi, I'm Alyssa. I'm on the thermo team with Liz and Andrew, and I'm going to talk about how we addressed our stretch goal, which was to do some empirical testing and get some data that would hopefully help to validate our CFD results. So the original plan was to print a full-size model of the heatsink, like here and here, and test it by pumping air through it in the wind tunnel that we have here at GCC. Unfortunately, we were unable to do that, first of all because the heatsink was just too big to fit in the testing chamber. And even if we had been able to size it down or somehow work around it, the junior lab had a specific setup that they didn't really want us messing with. And so instead of doing that, we decided to design and build our own custom wind tunnel. So you can see a picture here, and this is the actual thing right here. Very homemade looking, but it does the job. So it's made out of just some sturdy foam board and sealed with duct tape. We tried to seal it as thoroughly as possible because we did not want any airflow losses along the way for obvious reasons. So you can see we have an inlet and an outlet section that kind of taper down. Each of those is about 16 inches long. And then we have a flow straightener section on both the inlet and outlet side of the test chamber. Each of those is 11 inches long. And the purpose of having those there is to hopefully avoid any weird vortex effects and just have straight flow going into and coming out of the heatsink. So that was important. The testing chamber itself is in the middle. That's where the laptop is in the picture. And that was specifically designed to sort of mimic the type of enclosure that we were told would be around the heatsink in its actual use with BPMI. So it's fitted very tightly to the top of the fins and the sides of the base. We even added some extra material into the gap between the fins and the edge of the base so that the air wouldn't just go around. We wanted to force it to actually go through the fins. And then we pulled air through the heatsink from the inlet to the outlet side. There were basically three things we were asked to measure. We were asked to get pressure drop, obviously, air velocity, which would allow us to calculate CFM, and then to get an ambient temperature reading as well. So to measure the pressure drop, we have two barometers, one on each side of the testing chamber. You can see them in that picture on the right. And as you can see, we don't have them right up against the edges of the testing chamber. We have them spaced about 4 inches out. Again, that's to hopefully get them out of any weird vortex effects and just get them in straight flow. So we were able to measure pressures there and take the difference between them to find the pressure drop. To get the air velocity, we use this simple fan anemometer that you can see on the left. We placed that in the inlet at a position where we knew the overall area of the wind tunnel. And so we were able to use the velocity that we measured and the area that we knew to calculate the CFM and make sure that we were getting 60, 100, and 140 to simulate the actual performance. And then to measure the ambient temperature, we just used a simple thermocouple, placed it at the inlet, and got our reading there. So now I'm going to hand it off back to Andrew, and he's going to talk about printing the models for testing.
Okay, so in order to test these models, you have to find a way to manufacture them. As you can see from both these models, both of them are very large. So when we reached out to another company to print them, they were very expensive and would have eaten up a significant portion of our budget, as well as providing very lengthy lead times. So in order to counteract that, we printed everything in-house, and some of the adaptations we had to make to accommodate to this were we had to split everything into 1/4 of the heatsink in order to print 4 parts to put together. This is due to our on-campus printing capabilities and trying to print this model. So in order to connect this, we designed 4 holes into each section that were connected with dowel rods and glue to be able to keep them together for accurate testing. And as a final note, all of the tolerances and minimum feature sizes of these models can all be achieved in the final manufacturing process of direct metal laser sintering. Now I'll hand it off to Caleb to talk about some of our test results.
Hello, my name is Caleb, and once these models were printed, we were ready for testing. But in order to collect data for our testing, we were trying to collect pressure drop data. So the 2 barometers, we took the difference between them, and then we averaged them out, which can be seen as that yellow line. And for 60 CFM, we averaged a pressure drop of around 95 pascals, which is comparable to our CFD results. And we also eliminated outliers in the data if necessary. Engineers face lots of problems. We had our fair share on this project, but our main problem is up in the right-hand corner. We are trying to suck air through that whole distance in the front and get it to the back, which there's a big resistance from all those little fins going up and down. And this would it was challenging for us to get the air all the way through. We picked engineering professors' brains, and we thought about using mini computer fans. We even tried a big box fan, but then eventually we landed on a shop vac. We first tried a small shop vac, which had a small hose and little horsepower. We took the air filter off to see if we could achieve the CFM, which is the desired velocity to suck air through per BPMI specs, but the little one did not have enough. So that's when we went bigger, and we got the biggest shop vac that Ace had. And believe it or not, that was too much. So we had to throttle it. So we covered the inlet of the shop vac hose with duct tape. Also, our results from testing can be seen up here in this graph. We tested that design, which is the original, and then we tested a staggered airfoil design. But as you can see, our results on the airfoil were way better than the original, so much so you have to squint to see how low down our airfoil is, but our results were comparable to CFD results, and we were overall happy with how testing came out. And now Josue will come back up for next steps.
All right, so I got some news for your team that I know about. Actually, BPMI gave us 6 more months to work on the project. So we graduate. No, because of graduation, we're not allowed to work on the project after we graduate. Well, I might after I graduate. That's a different subject. So these next steps are pretty much saying if we had 6 more months, what we would do. The first thing on here is run full designs. Like said earlier, we couldn't really run full designs because our computing power was very small. It was mostly because of the original design. An eighth of that design would take about 64 gigs of RAM to run, and we don't have that much RAM here at the school or available to us. So to complete that task, to get more accurate results of the pressure drop and heat transfer of each heat sink, we were thinking about getting a supercomputer to hopefully run these computations. I think that would fit into our budget. We'll see if we're able to do that. Next is more of a mathematical approach. If we find an optimal number of pins and the size of pins instead of the guess and check we had to do. Unfortunately, we didn't have much time to actually run the CFD since I didn't get accurate results until about 2 months ago. So that was a difficult, so guess and check different sizes, what would happen. And the final step was to test more unique designs. So as you can see here, we have a lattice design. This is something we looked at very early on for research. As you guys can guess, this would be hard to model in Creo, especially after trying to model the original design. So it's something we would like to look at, but it was not very feasible for us to do in an amount of time. Another thing would take these airfoils and possibly cut indents into them, as it would give more surface area where most of the heat transfer would occur. But that was all for task 1. Now, next steps for task 2, like I said earlier during the schematic, we're supposed to minimize the height. If we had more time, we would look more at shrinking the height of the volume heat sink to see what would happen if the height decreased and how our designs would change. Unfortunately, we don't have enough time for that, but that's something we'll definitely look into. Next, we'll look more in depth in other shapes. You see when we worked with the ellipse, circles, and airfoils for the task 1 design, we had a good comparison. We would like to put those between the pin splitter plates to see how that compares up as well, and if our airfoil or ice cream cone designs will work well with that. And the last 2 things are pretty much similar to task 1, take a more mathematical approach instead of guessing and checking, and get to an answer as fast as possible and see if the mathematics were right compared to what we have. So now you know the next steps we would take. We'll give it over to Alyssa and she'll talk about the budget and how much money we spent on the project.
This is my favorite slide. I was in charge of making sure we didn't go over budget. My job was very easy. BPMI gave us a generous budget of $5,000, and our expenses, as you can see, we have about $278 for just printing the little heat sinks that we handed around to you, and then the big ones for testing, and then about $287 for testing equipment. Like Caleb said, most of that went towards getting the biggest shop vac that we could lay our hands on. But all of that comes out to just a little over 10% of our budget, so we were pretty happy about that. That is all. Thank you for coming, and we'll now take any questions that you have.